Hello, I'm here to present to you information on how to do linear programming. There are 4 steps that you should take, up to 4 steps you should take to do linear programming. The first step is to set up a linear system of the constraints, and that's if you're given a word problem. If you're not given a word problem and you're given inequalities and equations, they've already done step 1 for you. The second step is to graph the system of constraints, i.e. the linear system of constraints. The third step is to identify and shade the feasible region. And the last step is to find the solution, and it's on one of the boundary points, or you may hear the phrase corner points. So we're going to look at an example and do all 4 steps. So this example involves a calculator company who produces a scientific calculator and a graphing calculator. They have projections that indicate that they're going to need to supply at least 100 scientific calculators and 80 graphing calculators per day. And because of limitations on production capacity, no more than 200 scientific calculators and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. And each scientific calculator produces a $2 loss, and each graphing calculator produces a $5 profit. How many of each type should be made to maximize the net profits every day? Okay, so that's the problem, and we're going to be referring to it a lot. So back to our first step to set up the linear system. We're going to have 2 steps. The first step is to identify the unknown variables. And in this case, the unknown variables are the number of scientific calculators that need to be produced daily and the number of graphing calculators that need to be produced daily. And to make it a little bit easier, I'm going to let S represent the number of scientific calculators and G represent the number of graphing calculators that are produced daily. Okay. The second step is to, for each sentence involving the unknown variables, write an equation or an inequality describing the sentence or part of the sentence. And so that's going to take a little bit more work. So let's take a look at the first sentence. It says long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day, which means that the numbers for S and G, the numbers for S has to be at least 100 and the numbers for G have to be at least 80 for the daily production. Well, in order to do that, we use an inequality where this says that S has to be at least 100 and G has to be at least 80. All right. The second question or sentence talks about, because of limitations in productions, no more than 200 scientific and 170 graphing calculators can be made daily. So that means that the S number cannot be more than 200 and the G number cannot be more than 170. And so that is represented with these 2 sets of inequalities. The S number is less than or equal to 200 and the G number is less than or equal to 170. Okay, and so if we take a look at this, we see that there are some limitations with S in this group and there are some limitations with G in this group. Okay, and so the question is, how do we represent this as an inequality? Separately, you can represent them fine, but if you want to represent them together, we should combine the inequalities representing S and with one another. And so we end up with, okay, and this represents both of these, and this represents both of these. Okay, let's move on to the next sentence. It says, to satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. And it doesn't specify how many of scientific and how many of graphing. And so in order to represent that, we know that if we take the number of scientific calculators plus the number of graphing calculators and add them up together, that number should be at least 200. And this expression represents that. Okay. And the very last thing actually is not a constraint. It's going to be used to help us figure out which of our possible solutions will work. They want the fact that they want to maximize profit, which means they want to get the largest number possible. And the largest number possible, if each scientific calculator sold results in a $2 loss, but each graphing calculator so reducing their $5 profit. So combining the results from the sales of the scientific calculators and the graphing calculators will determine the profit. And so in this case, we use this expression of what we're trying to maximize, and we get the profit is equal to negative $2 times S plus $5 times G. I guess I should have put times G there. Okay. And that's what we're trying to figure out. What S and G will give me the largest profit. And if we're trying to minimize it, we try to find the S and G that gives me the minimum profit. So where do we get the potential S and G's from? Well, that's what step 2 is. Step 2 is to graph the system of constraints. And if you look at it, this is what we had from the previous page. The constraint on S, the constraint on G, and the constraint on the sum of S and G. So if I take a look at S has to be between 100 and 200. If S is on my x-axis, then this is at 100. Oops. And this is at 200. Exactly. So any point in this area would be sufficient. Any point. So what we're going to do is we're going to shade any point in this area will satisfy this constraint. The second constraint is a G constraint, which is G has to be a value between 80 and 170. So if this line represents all G values of 80 and this represents all G values of 170, then any point in between and on these two lines would be sufficient. And so any point in this region would suffice. Okay. And the last step is S plus G has to be greater than or equal to 200. So this line represents S plus G is equal to 200. How did I get that? I call it the finger method, which is in one case you covered up one of the shapes. In this case, if I cover up this, if I cover up, I don't know why this won't do it. I get that G has to be greater than or equal to 200. So that means here is G and here is G and any value above that would be fine. And if I cover up G, then that means S has to be any value less than or equal to 200. So it starts with here on the S axis and anything over there. So when I connect those two lump points, I get a line, and any area above this line would be sufficient. Okay. Now, even though we have the profit function we don't need to include because we're trying to figure out which are our possible S and G values. And all of our possible S and G values lie in areas that are including these constraints. Okay. So this is graphing the system, everything except the profit function. And so now let's go to the third step, which is identify and shade the feasible regions. So as you can see over here, we have the different regions that are feasible for each of the constraints, but the question is which region is feasible for all of the constraints. In other words, which area on this graph has both blue, purple, and orange. And that area looks like this shape right here. And this is the feasible region. Okay. And after we have the feasible region, then the very next step is to find the solution by it being on the corner points. So identify the corner points and then find the solution. So the first step for identifying the corner points is seeing where on the boundary where are the points that intersect two lines of our system. So this point right here intersects the orange line and the blue line. This point intersects the purple line and the blue line. This intersects the purple and the blue. This intersects the blue and the purple. This intersects the orange and the blue, but the purple is not around here, so we don't include that. That's not part of our feasible region. So we need points that intersect all three of our points, basically all three of our lines. And each one of these intersects or at points of all three different color lines, as you can see. So what are the coordinates of each point? Let's start with this point right here. Well, in this point, this line, orange line, meets with the blue line. And so S plus G is equal to 200, and this is S is equal to 100. So that must mean that at this point, S has to be 100. And if S is 100, then to get G, we replace S with 100 in this equation and get 100 there. So this point is the point 100, 100. Let's take a look at this point. In this point, it intersects the blue line, a blue line and a purple line. Well, the blue line is at S equals 100, and the purple line is at G equals 170. So therefore, we have our S and our G points. Our S point is 100, and our G point is 170. So we go around to each and every single one of these points, corners, and figure out its S and its G coordinate, and we can do that based off the constraints. And here we get 200 and 170. Here we get 170 for 200 for S and 80 for G. And then last but not least, for this one, it intersects the purple line, where the purple line is G is 80, but then it intersects the orange line, which is S plus G is equal to 200. So if G is 80, then S plus G, in order to be 200, we'll have that G is equal to 120. Oops, that is so wrong. That should be S. Sorry. S should be equal to 120. Okay? And we keep doing that, and now we have our points that are our corner points. And the next step is to evaluate the function. In this case, it's our profit function for each of these corner points, and figure out which of these corner points leads to the highest profit value in this particular problem. So for each of the points, we included their X coordinate and their S coordinate and their G coordinate and got a profit. S and G 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 got a profit. And the one that produced the largest profit was this point, 100 and 170. And that's our solution.